Hello everyone, welcome back to Professor Z Academy. In today's lecture we'll be covering superposition, and that's it. My entire house is currently asleep right now, so I'm going to have to be a little quieter than usual, so apologies. But we're going to talk about what exactly is superposition. So superposition refers to the idea that you can add electric fields to get the net field. What does that mean? So what's principle of superposition is that if I have a system of particles, let's say I have a positive particle and I have a negative particle, now there will be an electric field here, correct? Going from the positive to the negative. So the idea is that if I just have the positive, correct? Let's say at this point right here, which is equivalent to this point, the electric field is E1, pointing to the right. But then if I only have the negative, at that point, which is the same point that we're talking about, it'll have a value of E2, a field strength of E2. And what that means is that now when I bring these two particles together, the field here will have a value of E1 plus E2. And that's the basic general idea of superposition. So a more common example that you might see of superposition, or a more useful example, would be that of two infinitely long parallel plates. Or you can just use two parallel plates and approximate them to be infinite. So let's say I have two plates, one of them positively charged, and one of them negatively charged. And both of them have an equal charge or charge density. So, as you know, the field would go from here to here across the plate. So recall that we said that the field of strength for one plate would be sigma, the charge density, over 2 epsilon naught. And this was derived in the last video by Gauss's law. So what that means is this positive plate, if we have just this positive plate, at this point right here, the field strength is going to be sigma by 2 epsilon naught. But then the negative plate is also providing that same field strength of sigma by 2 epsilon naught to the right, since the distance from the plate doesn't matter for the field strength in this case. So it'd be sigma by 2 e naught plus sigma by 2 e naught, meaning that the field strength in the middle is equal to sigma by e naught, because if you add them up, that's what you get. On the other hand, if we go outside the plates, meaning not between them, here, at this point, the positive plate is pushing to the left with the value of sigma by 2 epsilon naught. Meanwhile, the negative plate is pulling to the right with the value of sigma by 2 e naught. So they cancel out, and the net charge anywhere outside the plates is 0. Now moving on, a more common example that you would see of superposition on the AP Physics C exams is that of nested conductors, or nested shells. So let's briefly review conductors. So a conductor, the most important rule of a conductor is that, rule number 1, the field inside a conductor is 0. Always, always, always. Regardless of the configuration, you will never get a situation where the field inside the conductor, and when I say inside, I should clarify, I mean inside the metal of a conductor, or like the material of the conductor. So when I say inside, I don't mean here. This is not what I mean. I mean this right here, in the actual material of the conductor. And that's because if there was a field inside the conductor, what that would mean is that there would be a free movement of the electrons inside, because conductors allow for the free movement of electrons. And if they move, they should create a counter current, which would because of induced current. So they should settle back to equilibrium, meaning the conductor has to be zero. And if the conductor is zero, also, the second thing, as a consequence of that, using Gauss's law, is that all charges of a conductor are on its surface, either the inner or the outer. In this, because it's a shell in this case, right? So it could be either on this inner, or it could be on this outer. And the reason for that is because if the field inside a conductor is zero, if we draw a small Gaussian surface inside, the charge enclosed should also be zero because the field is zero. Therefore, all the charges must be on its surface. So conductors are useful because they have a property known as shielding, electrostatic shielding. And what that means is you can basically treat a conductor like a closed room, because any field that comes from the outside will not impact what goes on inside the conductor. And here's why. When there's a field inside the conductor, it polarizes the charges on the conductor. And I need to emphasize that this property of shielding is only applicable to conductors. But there will be an induced charge. So let's say there's a field coming from this direction that I've indicated. That means that all the negative particles, negatively charged particles, will start gathering on the end where the field is coming from, and then the positive charges will be repelled. And again, it'll be on the surface. Also here will be some positive. Here there'll be some negative. And now what that means is now there's positive here, negative here, nothing stopping it in the middle. A field will also be produced from the positive to the negative inside the space enclosed by that shell. So then what happens? Let's call this E1. And let's call this, now if we continue this field, because it should go through the metal, it has a value of, let's say, E2. What happens is that the charges on the conductor configure themselves in such a way that E1 plus E2, or in this case E1 minus E2 because they're in opposing directions, is zero. And they perfectly configure themselves in that way, meaning that the net field inside the conductor, inside the space enclosed by the conductor, is zero. The outside world does not affect what happens in the inside. So you can basically treat it like a room, as I said before, where the outside charges absolutely do not impact what goes on inside. Right, so fields outside a conductor do not impact fields in the space enclosed by a conductor. So if we can treat it like a room, what do I mean by that? So what I'm trying to get at, essentially, is that if I have a bunch of particles on the outside, and then I have one positively charged particle on the inside, the electric field at a distance r away is still going to be kq over r squared, or whatever field value would be there, as if this entire configuration just didn't exist. So the field here is equivalent to if I just have some charge or something charged and just at a distance away, the field will be the exact same. So the inside is protected by the conductor from the outside. However, the outside is not protected from the inside. And what that means is, even though this particle isn't being influenced by these two, this particle still causes a force, still causes some influence over the outside particles. So because it's positive here, it'll start pushing away these positive charges. Which is a bit odd, but that's how it is. So now the last thing we need to talk about before we start diving into AP problems is the polarization of the shell, or the conductor, when there is a charge inside. So let me just draw a very big conductor, and I'm just increasing the thickness of it, and you'll see why. If I place a charge Q here, right, the charges inside the conductor are going to move somehow, meaning there's going to be negative on the outside, on the inside, towards the positive, and positive on the outside. Now the question is how? Like how much of the charge is on the inside, how much of the charge is on the outside? Well, we already know that the field inside a conductor is zero. So if I draw a Gaussian surface inside the conductor, like as so, since the field at every point on the boundary is zero, that means that when we take our Gaussian integral of EdA, the value of E is going to be zero for across the entire surface area, meaning that the charge enclosed also has to be zero. So what does that mean? It means that the value of the charge, the total charge that's enclosed on the surface of the inside, will be negative Q, or will opposite to the charge, such that the net charge in the center is zero. Make sure you understand that. Now you might be saying, what about the outside? How much charge does that have? Well, that's a matter of kind of simple math, right? If the conductor is uncharged, for example, then that means the net charge, which I'll denote with Q net, right? If the Q net is zero, what's going to happen, right? We have a negative Q here. Therefore, that means that the outside must have Q, right? Because the net charge is going to be the sum of all the charges on the conductor. So the inside has a charge of negative Q, and the outside must have a charge of Q, because Q minus Q is zero. However, if this isn't zero, right, let's call it Q net, this value is actually going to be Q net plus Q on the outside. And that's, again, a bit intuitive, because if we add up the inside charge of negative Q and the outside charge of plus Q, we're just going to get Q net, which is what we want, because there's a charge in the conductor. Okay, I think let's start diving into some APA FRQs. So the first one. A non-conducting sphere of uniform volume charge density is surrounded by a thin concentric conducting spherical shell shown in the cutout view. The sphere has a charge of negative Q, and the shell has a charge of plus 3Q. The radii of the inner sphere and the spherical shell are R and 4R respectively. Question A. Determine the charge on the outer surface of the shell. That's what we just discussed. So the sphere in the center has a charge of negative Q, right? So if I draw a Gaussian surface, let's draw it over here. Right? I'm going to expand the thickness of the shell. If I draw a Gaussian surface inside the metal of the shell, I need the charge enclosed to be zero, correct? Because the fields inside the metal of the conductor are zero. Therefore, the charge on the inside must be Q. But the shell has a charge of 3Q. Therefore, we want the sum of the charges to be 3Q. So 3Q is equal to charge in plus charge out, which means charge on the outer part of the shell. And we know that the inner is Q. Therefore, the charge on the outer part of the shell is 2Q. Question B. Using Gauss's law, derive an expression for the electric field at distance r from the center of the sphere for r is less than r. Express your answer in terms of Q, R, R, and a physical constant as appropriate. So this is something we discussed in the last video. And essentially the gist is that when you have a sphere of R, where R is less than R, it's a non-conducting, so it has a charge density. So let's R. Now this charge density is going to be the total charge, which is negative Q divided by 4/3 pi big R cubed. Okay, now for Gauss's law, we say that the integral of E dA is equal to the charge enclosed, which we can write as rho times 4/3 pi small r cubed. Also, this cube should be on the R. But 4/3 pi small r cubed, because the density times the sphere that we're in should be the total charge. So that's the charge enclosed divided by epsilon naught. Now E is constant, so this just becomes E times A, where A is the surface area of the sphere. And we can simplify this expression at the top to negative Q over E naught small r cubed over big R cubed. Now A, the surface area of a sphere, is 4 pi r squared. This is small r. Which means that if we simplify, what we get is E, because if we divide both sides by 4 pi small r squared, we'll get E is equal to negative Q over R cubed, big R cubed epsilon naught times R, just R to the 1. Great. Now for question C, the magnitude of the electric field at R equals R is 8. Calculate the value of electric field at R is equal to 2R. Now there's two ways to do this. So first of all, we know that we're outside of the sphere, meaning that we can basically approximate the sphere in the middle as a point charge in the center, because we're outside of it. So what that means is that we know that the electric field should be proportional to 1 over r squared, because that's Coulomb's law for point charge. So what we're doing is we're doubling the distance away. Therefore, we should be 1/4ing the electric field, meaning we'll get a value of 2. And yeah, that's the answer. The other way is to set out the whole equation, which is to say kq, or negative q, over r squared is equal to 2, is equal to 8. And then we're being asked to find k negative q over 2r, whole quantity 2r squared, which is 4r squared, which is 1/4 of our value. So we should still be getting 2. And D we'll discuss in a later video. Now for E. On the following axes that include regions 1, 2, and 3, sketch a graph of the electric field E as a function of the distance r from the center of the sphere. Okay. So part 1 is from 0 to r, which means inside the sphere. But in part B, we already derived a formula. And what we got was E is equal to negative q over 4 pi epsilon naught r cubed times r, right? So what we need to do is just graph this. So it's proportional to r, because this is all a constant. It's proportional to r and it's negative, meaning it should linearly decrease as the distance increases. So at r equals 0, we get 0, and this gets smaller as a linear function. Okay. Now, between r and 4r, we're outside of this main sphere, so we can approximate it as a point charge and simply use Coulomb's law, or which would just be, so the electric field for a point particle is just kq over r squared. So it'd be k negative q over r squared. So at some value, at r, it would be somewhere here. The electric field at that point should be continuous. And since it's 1 over r squared, it should be starting to approach 0. Right. So it'll be like this. It'll grow in a 1 over x squared fashion. And then the next thing is between 4r and infinity. So after we reach 4r, we're ignoring the thickness of the conductor. But technically, right at this point, at 4r, the value should be 0 because we're inside the conductor. But continuing onwards, between 4r and r, we can approximate this entire system, since they're all spheres, or spherical shells, etc. We can again approximate as a point charge in the center with the net charge of 2q, because the shell has a charge of 3q and this inside has a charge of negative q. We can approximate this as a point charge in the center with a charge of 2q. So which means that we'll have a discontinuity because our charge is now positive. So it'll be somewhere up here, and then it'll start decreasing and approaching 0 as r increases. Moving forward. Next question. A very long non-conducting cylinder, so we need to identify this as not a conductor, is surrounded by a thin concentric conducting cylindrical shell. Okay, so this is conducting. A segment of length L has a net charge of Q, uniformly distributed, and a segment of L on the outer charge has a net charge of 4Q. The radii of the inner cylinder and the outer shell are R and 3R, as shown. Determine the charge on the outer surface of the cylindrical shell within length L. So again, very similar to our last problem, to the first part of the last problem, which is if I increase the thickness of the conductor, just so I can get a scale, I draw in the center. So this has a charge of Q. So if I draw a Gaussian surface, once again, the charge on the inner part of the cylinder, right here, the total charge should be negative Q because there's no electric field, therefore the charge enclosed should be 0. So it's negative Q and Q. So that means, but we want the sum of the net charge to be 4Q. So we say 4Q is equal to the charge on the inner, which is negative Q, plus the charge on the outer, which is what we want. Which means our answer, by doing algebra, is going to be 5Q. Next question. Using Gauss's law, derive an expression for the electric field a distance r away from the center of the inner cylinder for r is less than r. Express your answer in terms of Q, R, R, L, physical constants as appropriate. Again, this is very similar to what we did in our last video with Gauss's law, but if we set up a Gaussian surface of another cylinder, inside the bigger cylinder. So this that was our Gaussian surface. This is our cylinder. So this has a distance of r, radius of r, outer one has a radius of big R. And the thing is, both of them have a length L. So we're being asked to find electric field. So the charge density in this case is going to be Q by pi big R squared L. So that means our charge enclosed is going to be pi small r squared L times the density. So pi cancel out, which leaves us with Q times r squared, small r squared, over big R squared. Okay, so let me just move over here. So we said that the charge enclosed is Q small r squared by big R squared. So now let's set up our Gaussian stuff. Integral of E dA is equal to this Q enclosed, which we know is Q by epsilon naught here, R squared by R squared, small r squared over big R squared. So now we know that the electric field is constant. Therefore, this integral just turns into EA is equal to Q over epsilon naught big R squared times R squared. Now in this case, A is the surface area of this cylinder, but it does not include the edges of the cylinder. And you might be asking why. That's because this goes on for infinity. Therefore, there can't be an electric field pointing out in the direction of the infinite direction. So it'll get canceled out. It's just zero there. So we ignore basically the gist is in whatever direction that it goes on for infinity, you ignore the electric field out of that direction. So there was another question in a previous FRQ that had an infinite slab with constant height going out in all four directions. But the height was constant. And what you do is you need to ignore the electric field. The electric field does not exist in this four directions where it's going on for infinity. It only goes up and down because those are not infinite. So meaning that in this case, the surface area is just going to be 2 pi small r times L. So this gives us an answer of Q by 2 pi epsilon naught L r squared times R. Okay. Now part C. The magnitude of the electric field at R equals R is 12. Calculate the value of the electric field at R equals 2R. Hey, pretty similar to our last question. So once again, the electric field is proportional to 1 over R squared. Because when we're outside of the cylinder, we can approximate it as a straight line at the center of the cylinder. So if we're moving out by, what are we doing? We are doubling, therefore we should be 1/4ing the electric field. So that should give us an answer of 3. Apologies, that's incorrect. This is not the answer. And the reason for that is, as I mentioned briefly, you approximate as a straight line, not as a particle. So this relationship does not hold. So if we approximate the cylinder as a straight line in the center, E is actually proportional to 1 over R. You might be asking why. And we derived this in our last video for a line of charge. But essentially, if I draw my Gaussian surface here, with some value R, what we get is that the electric field times 4 pi RL, 2 pi RL, it's going to be equivalent to the charge enclosed in that line by epsilon naught. So E is just Q over 2 pi R L, or 2 pi L E naught by R. And you see here, this is only 1 R in the denominator. So you have to be careful with questions like these, not to hastily jump to assumptions. I'd recommend definitely, if you either memorize for cylinder point particle, if you want to, but a more general approach would be drawing out that Gaussian surface to find it out. So if it's proportional to 1 over R, and we have a value of 12, and we double it, it should just be 6, which is the correct answer. So that's part C. Now part E. On the following axis, graph the electric field. So 1 is between 0 and R, which is inside the cylinder. So we already found a function for that as this. So Q over 2 pi epsilon naught L R squared is all constant, and it's just proportional to R. So it should be a linear function. Then in section 2, we found in part C that it's proportional to 1 over R. So it should be something like this. Then it momentarily goes to 0 because we're inside the conductor. But then at 3R, the charge jumps from Q to 5Q, right? Because now we're outside of both of these cylinders. So we can approximate it as a line of charge 5Q rather than Q. Meaning that the charge should jump up, again, the field strength should jump up, and once again decrease. Okay, now to our last question. A very long, solid, non-conducting cylinder of radius R has a positive charge of uniform density rho. This is a non-conducting cylinder. A section of the cylinder far from its ends is shown in the diagram above. Far from its ends is shown in the diagram above. Let R represent the radial distance from the axis of the cylinder. Express all answers in R rho and fundamental constants. Using Gauss's law, derive an expression for the magnitude of electric field at radius R is less than R. So, once again, Gaussian surface of a cylinder. So E times 4 pi, if we just cut out a little bit, 4 pi R L, 2 pi. I always mess it up. I messed it up in like 4 videos, but always correct it. So charge enclosed will be rho times pi little r squared L over epsilon naught. And because charge enclosed will just be the density times the volume. So the L's cancel out. And what we're left with is E, and also the pi's also cancel out. We're left with E is equal to rho by 2 epsilon naught times R. B, using Gauss's law, derive an expression for the electric field radius R is greater than R. Now in this case, there is no density, but there's no, the density, like the charge does not increase as we increase R. It's just constant. So our Gaussian surface, when it's a cylinder, we can approximate as a line of charge in the center. So we take our Gaussian surface, and our charge inside will be something like this. So if we just cut out a quick section of length L, we'll get that E times 2 pi RL is equal to rho times pi big R squared L, because now we're outside of the cylinder, over epsilon naught. So cancel out, cancel out, cancel out, cancel out. And what we're left with is E is equal to rho big R squared over 2 epsilon naught times 1 over R. So now part C is asking us to sketch out the field E. Okay. So we've derived an expression for inside, we've derived an expression for outside. Now we can put these to good use. For distance from R equals 0 to R equals 2R. Seems kind of weird. But for between 0 and R, we've derived that as rho over 2 epsilon naught is a constant. And the main gist is that's proportional to R. So it starts at 0 and it increases linearly. Now it should be continuous here, and it now decreases 1 over R. And it only asks us to draw from R to R, so it'll be something like this, and continue infinitely. So you might be saying, for all these last 3 questions, I've kept saying that it's continuous at this point, and you might be saying, why? Well, that's because the electric field at that point, so it should be identical. Since from the left, as we go from the left, we're increasing our R, and we're increasing the charge, right? Like, essentially, just at R, our 2 calculations are solving for the same thing. They should not be a discontinuity, because at that point, we're solving for the electric field on the boundary. Same with all the other ones. Here, the reason that it jumps up is because the charge suddenly increases, right, from Q to 4Q. But on both sides, the charge at that point is constant. The distance is constant. So that point should be the same. But here there's a discontinuity because we jumped up from Q to 5Q. And here we didn't. We just kept that same charge. And then same as here, there's no discontinuity. It's continuous at this point because the charge is the same, negative Q. But here we jump up to a value of 2Q in closed charge. So our field should also jump up in strength. And that's why there's a discontinuity. Now, the last question. The non-conducting cylinder is replaced with a conducting cylinder of the same shape and linear charge density. On the axis below, sketch the function E as a function of R. For R equals 0 to R, it's 2R. So if it's conducting, if you're inside the metal of a conductor, the charge, the field, will always be 0 inside the conductor. So from 0 to R, it's a flat line. Then from R to 2R, our calculations from B still apply, because if we just redo the calculations, we'll get the exact same result. E times 2 pi RL is equal to the charge density times the area by epsilon naught. That's the charge enclosed. So we should get it should jump up suddenly, and then once again be a function of 1 over R. And it'll be a little bit more steeper, but as long as you draw a function of 1 over R, you're good. Okay, that's it for this episode. Thank you all for watching, and I hope this helps you in your physics endeavors. Goodbye, and see you next time.